All right. Well, thank you very much. We're very excited to have Dr. Lindley Winslow joining us today. Dr. Winslow did her undergraduate work at the University of California, Berkeley in physics and astronomy. And she also got her master's there and her PhD also from the University of California at Berkeley. We're very excited to have her here. She is currently a professor at Massachusetts Institute of Technology and has quite an interesting background. So we're excited to have her give a talk today on neutrino physics. So take it away, Dr. Winslow.
So hello. Hello everyone. I'm so happy to be doing this. So as Bill said, I'm a professor here at MIT and I'm a neutrino physicist. One of the reasons I was excited to talk to you all because I wanted to first advertise that MIT has a summer research program. The applications are due, I forgot to look this up before talking to you, in January or February, and we're always completely undersubscribed in physics, and so it pays for you to fly, stay, and a stipend. So if you're interested at all, contact me afterwards. I am the only Lindley Winslow, period, especially if you have physics after it when Googling. So what I wanted to talk to you guys about today was my research. And as a fun opening, so I'm going to switch over now to sharing my screen, if that's okay.
Yes.
Does that look good?
Yep. Oh, perfect. Nice title slide. That is cool.
So I like to say that I'm one of the real Ghostbusters. And one of the fun things that happened to me was 2 summers ago, I helped actually with the filming of the most recent Ghostbusters here in Boston. And so just a little background on that, they sent me this weird email about this picture called Flapjack. And through it, I realized that it was actually the Ghostbusters reboot. And they wanted to understand what a real particle physics lab was. So they came and they looked at my lab. And this is what my lab looked like about 2 years ago. It was filled with a lot of, say, treasures from older faculty members. And so we showed them around and they were like, oh my gosh, it's as dirty as we expected. We wanted the film to be. We thought it should be cleaner. So we helped them in what the lab should look like. And if you guys have seen the movie, you'll see setups that look like this. And you'll notice that some of this stuff actually showed up on set. And so my junk turned into the part of the props that went into the movie.
So you're the real life Holtzman, huh?
Yes, exactly. Oh. And I'm okay with that. So I was pretty.
Oh, hell yeah.
So along the way, I also found them a postdoc. And so as we were touring around, they looked in one of the corners in my lab where another professor has a setup. And that's where Dr. James Maxwell works. And so he actually set up some, actually a mock-up of his physics experiment there. And then while I was there, they're like, well, maybe, could you tell us how this proton pack should work? So he actually did a redesign of the proton pack for them. And now it has superconducting magnets and everything. And they actually paid him to work on the movie. And not that you really have to pay a physicist to work on a science movie.
You do that for free. Wow.
And so then what did I do? So if you've seen the movie or seen the trailer, you'll notice this intro scene that's just filled with equations. And so what I can tell you is it's all right. In fact, it follows a derivation from the graduate textbook, Halsey and Martin for particle physics. And so what it is it's the derivation of the life of the proton in this theory called SU5. And it predicted that the proton should be on the order of 10 to the 29 years. And then an experiment, Super Kamiokande, measured it and set a limit of greater than 10 to the 30 years. So it ruled out this beautiful theory that everyone thought really should be true. But what I like about it is that the main background to this measurement was neutrinos, the experiment, the particle I love. And from it, we actually learned something about the neutrinos themselves. And I'll tell you a little bit about that today. And that's actually what won the Nobel Prize last year in physics, which was this effect called Neutrino Oscillation. That was discovered in Super Kamiokande when trying to disprove this theory. So that's why that's up on the board. And I can guarantee you it's all right, right there. So let's start getting into some physics. So much of the universe is actually pretty ghostly. So 70% is what we call dark energy, and we give it a name just so at least we don't have to admit that it doesn't even have a name. We really don't know what this stuff is. It's what's causing the universe to accelerate. 25% is this stuff that we know interacts gravitationally, and besides that, we don't know what it is, and that's called dark matter. And so then 4% of the universe is free hydrogen and helium just left over. And so then if you look at this little tiny piece of the pie, you start looking at what we actually know about. And so 0.5% of this is wrapped up in stars. 0.03% is heavy elements, i.e. what we're made out of. And then 0.3% of the universe are neutrinos. And so for something that you may or may not have heard about, that's a big fraction of the universe. And we actually don't know that much about neutrinos. After dark energy, dark matter, neutrinos are pretty unknown. So who are the real Ghostbusters at MIT? Well, including myself, I work within about a group of 30 particle physicists, but the ones that really are going after this physics is a theorist, Tracy Slatcher, who works on dark matter theory, my mentor, Janet Conrad, who is an experimental neutrino physicist like me, myself, and Tristan Perez, who is an experimental dark matter physicist. And so if you come and visit us, those are your real Ghostbusters. So let's actually go into this particle that I study. So what are neutrinos? So neutrinos are fundamental particles. This means that we don't think they're made up of anything else. You can't break them up into smaller things. And we refer to them by the Greek letter nu. And we love making jokes with things like, what's new? And yes, that's the one that came to mind right now. But yes, we make use of the bad puns with news all the time. So second, why are they special? So to understand why they're special, let me introduce you to all of the fundamental particles, i.e. the particles that we don't think you can break up into other things. And so this is the updated standard model of particle physics, everything we know about the universe. You can kind of think of this as the table of isotopes for particle physics. So our understanding of everything in the universe is divided up into quarks. So there's 6 quarks, the up, down, charm, strange, and top and bottom. There are 6 leptons. The one that you might know the most is the electron, and its heavier charged partners, the muon and the tau. And each of these charged leptons comes with a neutrino, the electron neutrino that goes with the electron, the muon neutrino that goes with the muon, and the tau neutrino that goes with the tau. And then we understand forces by the exchange of particles. And so the force you guys are most familiar with is probably the electromagnetic force, and that's understood by the exchange of photons. The strong force, what keeps together protons and neutrons, is explained by the gluon. And then the weak force, what dominates decays of, say, of nuclear isotopes and heavy fundamental heavy particles too, are the Z and the W. And so that's how I see the universe. That's my periodic table of the universe. So some of the first of the weird things, I said this a little bit, in particle physics we understand the forces of exchange of particles. The quarks, they stick together. We never see them by themselves, so you can think of them as being cliquish. They're always found in either 2s or 3s. And that's due to the nature of the strong force that holds them together. And finally, these leptons, they're independent, and they're the ones that you see out and about in the world. And so, once again, the electron is the one you know. They get this name lepton from Greek. It means small change. And so, like, these are like the little extra pennies that you find in your pockets. So, these leptons, they come in pairs. The electron with the electron neutrino, the muon with the muon neutrino, the tau with tau neutrino. And the charged lepton, goes with each neutrino, and we call these neutrinos flavors of neutrinos. And so it's the electron flavor, the muon flavor, and the tau flavor. So then let's get back to why these neutrinos are special within this model of particle physics. So the quarks and the charged leptons, they have charge. The neutrinos have no charge. Neutrinos only interact through this weak force, which means that they don't interact very much. So how to understand this? So something that interacts through the electromagnetic force, like an alpha particle that comes out of the decay of a heavy isotope, it can be stopped by a piece of paper. A beta particle, an electron that comes out of a nuclear decay, it can be stopped by a piece of plywood. A neutrino may or may not be stopped by a light year of lead. That's what it means to be weak interacting. So just try to wrap your head around that and what it means to be an experimental neutrino physicist and try to measure things about these particles that really don't care about a light year of lead in their way. So then the last part of this is when the standard model of particle physics was written down, we had no evidence of neutrino mass, so it was assumed that they were massless particles. So to answer the original question, they're special because they are the only ones with no charge, they interact only through this weak force, and they might be massless. And so at this point, you're like, this is kind of a boring particle. And so why are we going after them? And my little joke here is, if you know something about dark matter, is they're not WIMPs, but they are still interesting. And so why are they interesting? And that's answered by, where do we find them? So we find neutrinos anywhere where the weak force is important, especially in decay of particles and nuclei. So, like where? The sun. The sun is powered by a series of nuclear reactions that are, some of which are governed by the weak force, and each branch that powers the sun ends up making some characteristic neutrinos. And so that's actually one of the roots of neutrino study, was to prove that this is actually how the sun is powered. Another good, and so just to give you an idea of how many neutrinos the sun makes, 100 trillion neutrinos pass through you every second from the sun. And my guess is you haven't noticed that. Once again, they don't do much. So the other good place to find them is in nuclear reactors. As you can imagine, there's a lot of nuclear reactions in a nuclear reactor. How does a nuclear reactor work? Well, you have one neutron come in, it breaks apart a uranium-235 atom that then subsequently beta decays, usually making about 6 beta decays and 6 antineutrinos per fission. So if you have a commercial power reactor, so something on the order of a gigawatt of thermal power, which translates into a little less electrical power, you get 2 times 10 to the 20 neutrinos per second per gigawatt of power. So that's a lot of neutrinos if you happen to be sitting next to a nuclear reactor. So then the last big place where neutrinos were made was in the Big Bang. So the universe had so many energy that the neutrinos were constantly sort of interacting with each other and were so dense. Then about 2 seconds after the Big Bang, the universe cooled too much, and those neutrinos haven't had enough matter to interact with since then. So they've just been getting colder and colder as the universe expands. And this is actually a little bit before the photons. This is called decoupled. So they're actually colder than this cosmic microwave background. The cosmic neutrino background is about 1 degree colder. So then for every cubic foot in the universe, there are 10 million Big Bang neutrinos. So as we move around, we move through a sea of relic Big Bang neutrinos. So that's why there are so many neutrinos in this universe and why they basically equal the amount of matter in stars. And so just think about that for the second when you look up at the sky, that there are about the same number of neutrinos as stars in the sky as far as mass goes. So as you can imagine, just due to their sheer numbers, their physics is important. So the question is, what's new? And there I used my joke. So the answer is neutrinos have mass. And this is what the Nobel Prize last year was about. And so how did we prove that the neutrinos had mass? So once again, the neutrinos come in 3 flavors, electron, muon, and tau. And if they have a mass, that mass has to be small, otherwise we'd have seen evidence for it before. So we still have not directly observed neutrino mass, but we have observed something that's kind of even neater. So once again, neutrinos are a bit weird. So let's talk about what we mean when we talk about an electron. It's a particle with a mass of about 1/2 of a mega electron volt, and it has a charge of -1. So we identify the electron by its mass and its charge. Well, the neutrino doesn't have a mass and doesn't have a charge, so how do we define what a neutrino is? We define a neutrino as how it interacts. So if we see an interaction in our detector and an electron comes out, it was an electron neutrino that must have come in. And so that's different than what we say for an electron, where we have a mass and a charge, and we can actually probe that. With the neutrino, it has to interact, destroy itself, make something, and then that's how we figured out what had come in. So it's a fundamentally different way of defining a particle. So it can lead to some weird things. And so the basis of the quantum mechanics is that matter can be a particle and a wave. And if we're in that regime, what we have is we have this sort of electron-flavored neutrino wave that's created at this point. So we can write down a mixing of waves, and you can do the formal math here where you have mass states of neutrinos and flavor states of neutrinos, and they're not the same, and we relate them by a mixing matrix. And so we can express the electron neutrino as a superposition of mass states, cosine theta, sine theta telling you exactly how much of each mass state equals an electron neutrino. So we start with one wave, we've added another wave to it, and we end up with this effect, this interference pattern. This is called beats, and it's what you hear if you hear an orchestra tuning up and the instruments are slightly out of tune, you hear this wah sound. That's the beating effect, and that's basically what neutrinos are doing. You have these two waves that are very closely matched, but not quite, and you get this distinctive beating pattern. So if you're wanting to plot what the neutrino looks like as a function of space, at time t equals 0, you make some pure Nui beam or some pure flux of neutrinos out of a reactor. And the mass states propagate through space, doing their interference. And at any point along here, you're going to get a different mixture of these mass states and these flavor states until you come back, one whole period and come back to a pure Nui state. Because their masses are so small, this effect is coherent over long distances. And so effectively, neutrino oscillations is testing quantum mechanics over distances of hundreds and thousands of kilometers, which is kind of neat to think about. So if you actually write down the equation for neutrino oscillation, this is what it looks like. We have how much mixing between these states that we have. We have an effect due to the energy of the neutrinos, how far the neutrinos have gone, and the mass difference squared between the neutrino states. And that's the key. If you observe this effect of neutrino oscillations, the neutrinos must have mass. So this is data from the CAMLAND experiment. So on the y-axis of this plot is survival probability, basically the number of observed neutrinos versus the number we expected. Therefore, the probability that it didn't oscillate over plotted as a function of L over E. And what you can see by eye is that it has this sinusoidal pattern. It's not a perfect sinusoid because there were a lot of different sources that went into it, but it's very obviously a sine pattern. And that tells us that really we have a delta M squared. Neutrinos are oscillating and they have a frequency that corresponds to about 7 times 10 to the minus 5 electron volts squared. So this data came by using every single nuclear reactor in Japan and detecting all those neutrinos with a 1 kiloton scale detector of liquid scintillator. And so this worked by the neutrino came in, hit a proton, made a positron, and we saw the light do that positron vibrating molecules in the volume. And we saw the light that came out from the de-excitation with the photomultiplier tubes. So this is a really big detector. It's about the size of a small apartment building. And so here you see a picture of me as a graduate student standing on top of the detector, kind of where the cartoon dude is standing, right below him. So that gives you a scale of the idea of how big these detectors have to be to make some sense of neutrinos since they interact so little. And so then that is the data once again. So we observe neutrino oscillation, therefore neutrinos have mass. And that was the Nobel Prize of last year. And it also gave a breakthrough prize. This is the prize that's awarded by Silicon Valley now. It's actually more money than the Nobel Prize, and it gets shared among the whole collaboration. So there you see on stage the founder of my experiment. So now that neutrinos have mass, things actually get even more interesting. So what you now should ask differentiates an electron and a positron. A positron's an anti-electron. It's the antimatter version of the electron. So it's the fact that it has opposite charge. So the neutrino has no charge. So is there any reason the neutrino could not be its own antiparticle? And so if the neutrino is its own antiparticle, how do we prove that the neutrino is its own antiparticle? This is called a Majorana particle, named after an Italian physicist. And there's a nice whole backstory to that I can tell you about another time. So let me tell you a little bit about how we're going to do this test. Because the neutrino, if it's its own antiparticle, has really deep consequences to the early universe in explaining why there's more matter than antimatter. So let's have a little lesson in nuclear physics for a second. So this is beta decay. Beta is another word for an electron. So the neutron decays to a proton, spitting out an electron to balance charge and an antineutrino to conserve lepton number, to conserve the amount of matter and antimatter. So this usually takes place in the nucleus, where you have Z number of protons and A number of neutrons plus protons. And so when the beta decay happens, you get a Z plus 1 and A remains the same, and the electron and the antineutrino pop out. So this process is called double beta decay. So what happens is two protons simultaneously decay, spitting out two electrons, two antineutrinos, and the charge of the nucleus goes up by 2. The change here in matter and antimatter, the number of leptons, is still the same. It's still 0. So this can happen in some nuclei where, if you look at this level diagram, this tells you the energy of the states, where the daughter nucleus is actually heavier or more energetically forbidden compared to the mother nucleus. And so in order for this process to happen, the nucleus needs to actually effectively decay to its granddaughter. It needs to spit out these two electrons in order to get to a more bound state, a lower energy state. So this is something that's allowed. It's hard to occur, but we know it happens, and we've actually measured it happening. And so here's a cartoon picture of particle physicists viewing this. You have some the black box of neutrino physics, the two electrons coming out and the two antineutrinos. And it was first calculated actually in the 30s by Maria Goeppert-Mayer, who went on to win the Nobel Prize in physics for the shell model of the nucleus. And that's her winning her Nobel Prize and being led by the King of Sweden. So we know that this can happen. And so this is what it looks like in your detector. You sum up the energy of those two electrons, and it looks like a standard beta decay spectrum, where you have this sharing of energy between the electrons and the neutrinos. So there's another process that can happen called Neutrinoless double beta decay, where no neutrinos come out. And the change in the number of leptons here is +2. You made more matter than antimatter, and that's really exciting. So this also tells us that the neutrino is its own antiparticle. And so now I'm showing you the cartoon picture of basically the antineutrino becoming the neutrino and getting sucked back into the reaction. And that's how we prove that the neutrino is its own antiparticle. And that's how we make more matter than antimatter. That's one way to do it. And so this is why we're really excited about this, and why I spent so much of my time looking for this one nuclear process. So this is what the experiment looks like in your detector. So here you have the dotted line, which is the 2 neutrino double beta decay, the allowed process. And since now you have no neutrinos coming out, those 2 electrons need to sum up to the total energy of the decay. So you end up with this extra peak of events at the end, at the high energy tail of your 2 neutrino spectrum. And so we know exactly where to look for this effect. So now the question is, how do we actually build a detector to see this? And so we actually come back to CamLand at this point. So this is a very simple experiment where we've taken the old CamLand detector, and inside the big balloon that was the target for the reactor neutrino experiment, we put a little mini balloon and filled it with xenon-doped liquid scintillator. So the xenon-136 is the isotope that can do this rare neutrinoless double beta decay process. And so we measure the total amount of energy deposited in the detector. And so you see on the x-axis of this plot, the visible energy, the sum of those 2 electron energies. And there's a bunch of stuff that can mimic it. But you see here, the dominant process is this 2 neutrino, this allowed double beta decay. And so we're able to measure this 2 neutrino process, and it's the slowest process ever directly measured, on the order of 10 to the 21 years. And so wrap your head around that for a second. It's more than 10 orders of magnitude larger than the age of the universe. So what we don't see is any evidence of the 0 neutrino, the neutrinoless double beta decay, the process that we really like. And so we set a limit that this process must be longer than 10 to the 25 years. And so now we're trying to improve the experiment. So some of my undergraduates went to Japan in 2015 to build a new mini balloon, a cleaner, lower background balloon. We also tried to do some improvements of the detector. So this is another student of mine and one of my Japanese colleagues in a boat fixing the outer water veto detector. And you can see below the boat this white curving structure. That's the outer part of the sphere curving down below. And here they are at the bottom of the detector once they fixed all the PMTs and drained all the water. So you see the bottom of the sphere and them smiling around the last photomultiplier tube being replaced. So then the other experiment that I'm working on is Core. And so this is a different technique for going after this rare nuclear process. And it's super cool. And I mean, it's really super cool. So it's a bolometer. And what's a bolometer? A bolometer is a detector that you cool down to 10 millikelvin. And so if you guys know the temperature of the universe at 2.7 Kelvin, we are now, once again, 2 orders of magnitude colder than the universe. And so at this temperature, you can actually see the change in temperature of the crystal due to 2 electrons passing through the crystal. It's 0.1 millikelvin on 10 millikelvin. That's why we have to be so cold. And so that's how a bolometer works. And it's very precise at measuring energy depositions in these crystals. And so that's what Core is. We're going to take 1,000 tellurium dioxide crystals. Tellurium-130 is a double beta decay candidate. And we're going to put it in a dilution refrigerator. That's what this big thing is. And it cools it all down to 10 millikelvin. And when it's cold, it will be the coldest cubic meter in the known universe. And if we're not the coldest cubic meter in the known universe, then we've discovered aliens and we're okay with no longer being the coldest cubic meter in the universe. And so we are cooling down actually as we speak. And so Core is actually the latest experiment. And you don't start with 1,000 crystals. You start with actually like 1 or 2 crystals. You move to a tower, you make a better tower, and then you make 19 towers of crystals. And so that's what we finished this summer. And so this is what the detector looked like at the end of August. And there's a pretty picture looking up from below, so you believe me that there's 19 towers of these pretty sort of smoky colored tellurium dioxide crystals. And so now we're doing the final checks on this refrigerator. This is my postdoc, Lucia Canonica, looking over this very complex machine. And we're expecting first data in early 2017. It takes about a month to cool this thing down. And so hopefully they turned the switch this week. But I haven't heard the final word as whether it happened or whether they're still doing some double checks. And it's about 6 tons of material. It's 1 ton of crystals, and then all the surrounding stuff needs to be cooled too. And so it's quite a bit. It's quite an impressive achievement, just this refrigerator that you see here. So the sort of tagline for this is, we are preparing for more ghostbusting. The neutrinos have given up one secret, namely that they actually have mass. And now we're really going after, with several approaches, whether they're their own antiparticle and that they can explain these deeper issues in the universe, namely the matter-antimatter asymmetry, or the bigger question of really why we're here. And so that is the summary of my research. And I was hoping that you guys would have some questions. And so there's my group. And once again, we would love to have you this summer and add you to our list of wonderful undergraduates that helped with this detector.
Cool. Let's give our speaker a round of applause. All right. Do we have any questions? All right, Charles, what you got?
You said it was called a bolometer? Is that
a bolometer, B-O-L-O-M-E-T-E-R, so meter, bolometer, bolometer.
I was wondering how, if you could, briefly explain how you're able to get that so cold.
So it's a dilution refrigerator. So this is really neat. So what you do, a normal refrigerator, you do this cycle where you sort of pump on a gas and you use the phase transition between liquid and gas to pull heat out of the refrigerator. What we do here is, instead of like a normal refrigerant that you have in your refrigerator, we pump on a mixture of helium-3 and helium-4. And there's a phase transition that happens between these 2 gases when they go superfluid. And it's that phase transition that we use to pull heat out of the copper plate, and then we cool that copper plate and we cool everything else from thermal contact with that copper plate. And that's how a dilution refrigerator works. So I am the proud owner in my lab of 20 liters of helium-3 and some other amount of helium-4, probably another 50%. And that's what we run around. I think Core's dilution refrigerator is on the order of 40 or 50 liters of this mixture.
Where is that experiment? Is it there at MIT or is it in Japan?
So the Core experiment is in Italy. When we run these very sensitive detectors, we can't do it at the surface because, as you may or may not know, the surface is constantly being bombarded by particles, where high-energy protons from outer space hit the upper atmosphere, making particle showers. And so if you put out your hand, you're getting like 1 per second to your hand, and that completely swamps anything relative to what we need to measure. When you're measuring something on the order of 10 to the 26 years, to give you an idea, that's less than 1 event per ton of material per year in the region of interest.
So how deep is it?
So the Corey experiment is 3,200 meters water equivalent. So it's about a mile down. It's it's a highway tunnel. It, quite literally, if you think of the boot of Italy, you drive from Rome to the other side, that's the tunnel you take. And so when they built it, they built some extra tunnels to do science in.
That is really cool.
Yeah.
I don't know that.
Mm-hmm. And so on the other side, Camland's in an actual mine. It's the one of the oldest mine in Japan. They've been mining it since 500 AD, and they pulled everything out of this mine that they possibly could, from gold to most recently cadmium and nickel. Sorry, nickel was the last thing they mined. And so that is where I have a mine driver's license, because that, once again, it's a horizontal access. And you get certified to drive these Toyota Land Cruisers that are specially fortified into the mine. So there's an element of adventure here, and I didn't tell you about neutrino experiments that are in Antarctica. So that's like your one legitimate reason to go to Antarctica, is to go do neutrino physics.
So is that the ice cube experiment?
That's the ice cube, yeah. And one of my postdocs worked on ice cube, and I'm very jealous of her pictures of herself at the South Pole. I need to figure out
what physics is ice cube looking at that's different from what you just described?
Right, and so I told you guys about neutrinos and how they're made anywhere where nuclear reactions are important. And so there's places in the universe where we have these particle accelerators, the jets that come out of black holes, and they accelerate these particles up to peta-electron volts, and even higher than that. So the Large Hadron Collider here is TeV, 10 to the 12, and so here you're talking 10 to the 15, 10 to the 18 electron volts. These super high energy neutrinos, and we would like to understand these cosmic accelerators. And so that's what IceCube was built. The flux is low, so you need to be really big, so they're using the ice as the detector. And so they drilled down with a water bit and sent these 1 kilometer long chains of photodetectors, and they actually used the ice as their target mass. And their big result is they saw the first neutrinos that they think aren't from our galaxy. So that was the really exciting result. About 2 years ago, they got eclipsed by the Nobel Prize in Physics last year. And then gravitational wave detection this year.
Yeah.
But the combination of IceCube and LIGO seeing these things, it's what we call the age of multi-messenger astronomy. For the first time, we have handles on astronomy that aren't light. And as a neutrino physicist, like, this is what they've been talking about since I was sitting where you guys are. And it's really exciting. And so if you combine that with my research, which I think is really exciting, really going after this the matter-antimatter asymmetry, neutrinos are kind of really where it's at. Neutrinos and gravitational waves, I'll give them that.
So do you feel like these sorts of experiments will kind of allow or move us away from looking at high energy accelerators and move us into being able to do cosmology and physics using these kind of detectors that don't require slamming things together? Right.
There's in a lot of ways they're complementary. My approach is to let the universe spend the energy to make the particles. And so I just instrument big amounts of stuff, if you haven't figured that out, and wait for something to happen. Versus you can force something to happen and force it to sometimes to happen at a higher rate if you actively collide things together. So it's all very complementary. But I do think we are sort of heading into a new direction as it becomes harder to make bigger and bigger machines, of how to more smartly use what the universe is already giving us. And we're definitely on that path. And that is, so among physicists, why we're so excited about the gravitational wave discovery. It's a new tool that we've sort of been dreaming about for 30 years or so.
For these neutrinos that you look at, do you look for what kind of neutrino they are, like electron neutrino or muon or tau?
Yeah, so the way you've designed your detector determines which flavor neutrino you're sensitive to. And so the CAMLAN detector is only sensitive to electron antineutrinos because we're looking for this interaction of the electron antineutrino on a proton making a positron. If you add different elements, you can see all of the neutrino flavors. And if you move to higher energies, you can see the tau neutrino. The tau neutrino is actually really heavy, so it doesn't show up in these lower energy nuclear reactions that I see. So
do you have bubble chambers attached in there?
So that was how some of the early reactions on neutrino were done. The bubble chamber is hard to scale up to large sizes. That's why you see this liquid scintillator detector. And so we lose the tracking information that you get in the bubble chamber, but we get just the huge volume so that we can actually get statistics to do the experiments that we need. So yeah, so the CAMLAN detector there, that's 1 kiloton of liquid, and the largest bubble chambers were sort of on the order maybe of a ton. So you get that factor of 1,000. That's the trick.
That's the trick. What about, so you're an experimentalist and you're working on some really cool projects. What sort of openings do you see in either your lab or at these projects for engineers that might be interested in like engineering physics or some hands-on applied physics?
Right, and so the border. So when we build these detectors, we need really good engineers too, because we're always pushing the edge of what can be done. And so that's kind of what I see our role as, is whenever some new technology comes out, physicists are like, oh, how can we use that? And we're often the first adopters, whether it's a new platform for computing, which is the great example of the early Macs that the World Wide Web was first written on, to me, where I'm really pushing the bounds of how fast a waveform digitizer, the Flash ADC can work. So one of my R&D projects is picosecond timing on these large-scale liquid scintillator detectors. And so that means that you need a digital oscilloscope on every single channel. And so how do you do that? And then on sort of the mechanical side, there's a lot of effort into how do you physically support something like this, and do you worry about thermal gradients in the detector? And then there's engineering on how do you build magnets, and so that's a little outside of what I do, but how do you make magnets with huge fields? And so we really push the edges of what you can do with magnets, and then that has applications to sort of MRI technology and what have you. So a lot of the engineers work in the national labs. And so the big ones are Oak Ridge National Lab in Tennessee, PNNL National Lab up in Eastern Washington, Lawrence Berkeley Lab in the Bay Area, Lawrence Livermore Lab, and Los Alamos National Lab. And then there's some smaller national labs, the Magnet Lab in Florida. And then, I forgot one of the big ones, and then J Lab, which is in Virginia, and Newport News, Virginia. And so that's where a lot of the engineering happens in the US. There's other places in the world where you have the engineers working too.
So how expensive is the liquid helium that you have to get?
So it depends whether you buy it through the Department of Energy or whether you buy it on the open market. So it's it's very important for building neutron detectors, and so it has national security applications. So it's actually a controlled substance. So if you try to buy it on the open market, my dilution refrigerator was $75,000 of helium-3. If you buy it for research purposes as a Department of Energy group, then you can buy it for $15,000. And so that's the advantage of being a research organization.
I was wondering if international students can join the research.
Definitely. So if you're asking about graduate school, MIT is a private school. So as far as we're concerned, we treat international and domestic students the same. You're all evaluated on your own criteria. For the summer research program, I believe you do not need to be a citizen to be to take part in the MSRP program. But I can check on that. Once again, and since it's an MIT-run program, citizenship can be waived.
Okay.
So I guess it's kind of a personal question. How exactly did you get interested in doing neutrino physics?
So it's one of those sort of rambling paths. When I was in high school, I thought I wanted to be a veterinarian, and then I had this crisis of animals dying, and that really I didn't want to deal with that. It was not hugging puppies all the time. So it's one of those things. I was pretty good at science, and I liked stars. I thought they were cool, and I was like, why don't I major in astronomy? And it turns out that I wasn't very good at astronomy, but I was actually pretty good at physics. And I had a postdoc who had worked on one of these large liquid detectors. And I was just fascinated by this interplay between sort of pushing the bounds of what you can do with detectors and doing particle physics here on Earth that can explain, the early universe. And it just really caught my imagination. And what I particularly like about my job is the fact that it's not the same every day. I really move between programming and, mechanical design, electronics, and I get to do everything. I'm not very good at everything. I'm like 50% of like 3 different kinds of engineers. But it's really fun on a daily basis, not to mention, I really enjoy teaching students. And so my job is pretty fun.
What part of the world are you from? Where do you originate?
I am from Wilmington, Delaware.
Delaware, okay.
And then, and I had lived there my whole life, and so I decided I really wanted to go to college in California, and I liked it a lot, and I stayed there. And then MIT made an offer I couldn't refuse. And so now I live on the outskirts of Boston with enough land that my husband doesn't have to see the neighbors, and that makes him happy.
Cool. How did the Ghostbusters team look you up and find you? What was the connection there? How did they know to find you?
Oh, right. So I had been a professor. I did have a 2-year break from MIT where I was a professor at UCLA in Los Angeles. And so if you guys have ever watched The Big Bang Theory, they actually have a science advisor. This was more important early on where they talked about science a little more. His name is David Saltzberg, and he's a particle physicist too. He actually works on these ultra-high energy neutrino experiments in addition to CMS at the LHC. And so they originally had approached him because everyone in Hollywood knows him now. He is like the go-to physicist now. And they're like, we're filming in Boston. He's like, I'm not in Boston, but my friend and colleague Lindley is. You should look her up. And so they emailed me. And that's why I didn't ignore the email, is they used David's name. And I'm like, okay.
This is legit.
This is legit.
Cool. That was really neat. Have y'all seen the new Ghostbusters? You haven't? Yeah. Go. You have. So SBS, we'll have to check it out, and then we'll watch it sometime. But maybe over finals week.
But yes, and so you can pause it at the board with all the equations and see if you understand it. And if you look at one of the other lab scenes, a picture of the picture of the bolometer I showed you, the diagram is up on the board.
Cool.
So if you're the one doing the board, you get to decide what goes up.
We got to find all the teasers in there.
Yeah.
Now we can watch it, pause it, and start explaining it to her.
That's right. That's right. We watched her seminar again so we can pay attention. Do we have any other questions for our speaker? No? Well, thank you very much. Let's give our speaker a round of applause.
Thank you, guys. It was delightful talking to you. And once again, I am the only Lindley Winslow. Please email me. I would love to see you guys at MIT next summer.
Cool. Thank you very much. I really appreciate your time. This has been amazing.
Thank you, guys. Have a good evening. Bye.
Bye-bye.